Hi everyone and welcome to another lecture. Today we want to talk about sum, direct sum and direct products of vectors. So we are going to start with discussing what do we mean by a sum. So as you can see, I've already written that. Let's say we have a vector space called V and it has two subspaces of V, that is U and W, and let me just use our old bracket notation to write them up. So what we're going to do now is that this subspace U will have elements something as U1, U2, U3, belongs to U, and similarly we'll have W1, W2, that will belong to the W subspace. And for any U belongs to capital U, that is any U from here, that is, okay, let's label this. This is 1, this is 2. Any U from U, capital U, or the U subspace, that is from 1, and any W from 2, if you take them and if you add them, that is, let's take U1, oops, it looks like V, U1, excuse me for that, U1, W1, and you want to add U2, W2. If you do it, then the resulting thing will belong to a vector space U plus W. And if you have some constant, let's say C, I mean not constant, sorry, a scalar. Let's say if you have a scalar C that belongs to the K over which these vector fields are defined, then you can write C times U1 W1, and this will belong to C U1 C W1, and the whole thing will belong to U plus W. So this is the idea for the sum, that is, you are just taking two subspaces and using two subspaces you are building up another vector space, that is this U plus W marked over here. So this is another vector space. And you might think that since I'm taking two subspaces and I'm adding them, so it's like taking two spaces and adding them together, and it should give me the vector space V, right? You might think that, but that is the idea of the direct sum, and this is just sum. So let's take an example and let's try to see how this thing works. So let's go for our usual 3D Euclidean space. This is X, Y, Z. It is easily verified that this 3D Euclidean space will form a vector space. And now you can think of two subsets, one of them being this elements on the x-axis, and the other is the element of the y-axis, and the other as the element of the z-axis. And if you just forget about the z-axis, that is, just forget about them, let's write forget z-axis. And now if you just glue this x and y together, you get the xy plane, but not the xyz space, that is the three-dimensional Euclidean space. So this idea over here, where we used U subspace and W subspace to form a new vector space, is similar to this example over here. And now we will see what is a direct sum. So let's write it down first. Direct sum. So again, here we are gonna use those two subspaces, that is U and W, and we are going to say that and we're going to say that the direct sum of u and w is for every element of V. Okay, you know what, let me just write it down. So let's try to write it down. We shall say that V is a direct sum of u and w if for every element vi, or you can just write small v, that belongs to the vector space V, there is a unique decomposition of V in terms of U that belongs to the subspace U and W that belongs to the subspace W. So what does this mean? That means we can write V as a sum of U, small u and small w, I mean the ket u and ket w. So the seemingly same thing, that is this direct sum and the sum we discussed above, but the only difference here is that in here you have a unique decomposition, that is this u and w's are unique. So let me highlight it down here. U and W are unique, right? And there is a very important theorem that we are going to talk about, but we won't see the proof, we will just take it without the proof. So this is a theorem, and it says that if you have a vector field over K, that is a Vk, and note that so far up until now we are only talking about finite dimensional spaces. So even though I'm not mentioning it explicitly, these are all finite dimensional vector spaces that we're dealing with, and this vector space has two subspaces, that is subspace U and W again. So let's take them to be U and W. And if we demand that U intersected with W is just the zero vector itself, that is you are taking all the elements of U and you are taking all the elements of W, and you are trying to find out which is the common element and you want to bring a set. That's what we mean by intersection, right? And the only element that is in common with these two subspaces is the zero vector, because by the very definition of subspace, each and every subspace must have this zero vector. So if this is the case, that is if our demand is fulfilled, then we can say that U plus W equals to V. That is, V is the direct sum of the subspaces U and W. So let's take this example again, that is with our 3D Euclidean space. So this is X, Y and Z. So if you just compose them into the XY plane plus the Z axis, this is a example of a direct sum, that is you had this XY plane and then you are adding another Z axis. So because you can see that if these two subspaces have nothing in common apart from the origin, that is the zero, or so to say the zero vector, right? They have nothing in common, And in fact, you could break it down even further by saying that this is my X, this is the Y subspace, and finally this was the Z subspace. So this is an example of a direct sum thing, direct sum stuff that we talked about. And you can even do direct sum of matrices as well. So I'll just show you direct sum of matrices. Let's say you have a matrix called 1, 2, 3, 4, and you have another matrix B is equals to 1, 9, 0, 0, 4, 5, 1, 1, 1, and the direct sum is denoted by this symbol. You put a plus and then you circle it. So this is the direct sum symbol. So we want to evaluate what is A direct sum B. We ask, what is this? The way this is defined is the following. So you take this matrix and you take this matrix, okay? So this A plus B thing is just A over here, B over here, and all the elements over here will be 0. So if you write it explicitly, A was 1, 2, 3, 4, right? 1, 2, 3, 4. B was 190. So write 190. Then 0, 4, 5, 0, 4, 5, and finally it's 1, 1, 1. So, and then all these blocks. So these are now sometimes called the block diagonal matrices. In fact, this is the name. It's a block highlighted with the blue mark. So these are called block, and these blocks can have any order depending on what you're adding, but the other elements will be as the follows. Here you have 2 and here you have 3, so you have to put 1, 2, 3 zeros, and there is 3, 4, and there is 3 more columns over here, right? So this is 0, 0, 0, and finally you have 0, 0, 0, 0, 0, 0. Now if you just look at this A and B here, you can see that this is a 4-dimensional matrix, and this is a 9-dimensional matrix. Obviously I'm considering these 2 zeros as well, but if I don't do that, then it will be a 7-dimensional, but let's keep it that way. And here this A plus B, though it seems it's a 25-dimensional thing, it is not. It's actually a 13-dimensional thing. Why? Because I can always decompose it into, let's say, 1, 2, 3, 4. This is one element type of thing over here, and I can write it like this, and all these zeros, they will correspond to some element 2, and finally this 3 by 3 190 0 4 5 1 1 1, and this will correspond to some matrix called 3. Obviously I cannot write it like this, I have to expand it a bit more, but this is one way to compactly write it, and this should give me, okay, let me just get rid of it. This is also a 13-dimensional matrix, and it can be proven in general. It can be proven in general that if you have a vector space V, its dimension is equals to the dimension of the subspaces that you are considering. That is, if you have subspaces as Vi, where I starts from, let's say, 1, 2, 3, and you also have to consider the fact that all of these subspaces have nothing but the 0 vector in common, then dimension of V is just the sum over dimension of Vi. So let's now talk about direct products. So let's say you have two vector spaces U and W, and these are not necessarily subspace of any vector space. It can be, but not necessarily. So we are considering the whole general thing. So we denote U cross W as the direct product, or if you talk in the language of sets, then okay, let me just write it down, direct product. Then we say that the set of all pairs, that is this U cross W is just the set of all pairs UW. Oops, I forgot to this kind of notations. Yeah, whose first component is an element of U and the second component is an element of W. So this is similar to a Cartesian product that you are familiar with from theory of sets and stuff. So now we say that if I have something called U1 and W1, and they belong to this giant space U cross W, and I have this U2 W2 that belongs to U cross W as well, then I can prove easily that this U cross W is a vector space itself. And after we prove that this is a vector space, we can immediately verify that this product is called a direct product. And when we talk about direct sum and direct product, we find a very close relationship with direct sum and direct product. And here we will just take it without proof. That is the fact that I am stating. The dimension of this direct product space is equals to the dimension of U and the dimension of W. So this is how I know this is a very short discussion and some of the things might be a bit dense, but the main idea is to understand this relationship that you will often see in your group theory books or in a Lie algebra book or in any quantum field theory or quantum mechanics book. So this will be it for today, and thank you.